Welcome back. In the last part of this lecture we're going to look at interaction forces, trying to understand where adhesion and cohesion actually comes from. If you've been following the diagrams I've shown you already, you should see that two materials in close contact are only interacting through their surface. And so what that means is the force of adhesion or cohesion is in some way related to the energy of that surface, and it has a special name. Unsurprisingly, it's called surface energy. And where does surface energy come from? It comes from a number of different factors: what the chemistry of the molecule is, and also how those molecules are arranged at the surface. And all of those things contribute to the overall surface energy of a material. Surface energy is a really complicated concept, and we don't need to go into it in super great detail. We just need to understand the basics of adhesion and cohesion so we can understand how dry powder inhalers actually work. The first thing we need to consider is, what is a surface? Now that might sound like a completely dumb question. Everyone knows what a surface is. A surface is at the top of a material, and that's absolutely true. But it does actually have a mathematical definition, as so many things do. So it's defined mathematically as an extended two-dimensional outer boundary of a three-dimensional object, or when I learned mathematics the technical term was a net. So on the screen in front of you, you can see on the left hand side a cube, and on the right hand side you can see the surfaces of those cubes laid out as a net, and that is the surface as a mathematical definition. That mathematical definition, which is two dimensions, presumes an infinitely thin layer at the surface of our material, and the reality of the situation is a surface can really be considered as a number of molecules thick. So usually people consider maybe 100 to 200 nanometers of thickness to be the actual surface of a material. I suppose one way of thinking about that is that the molecules in the core of a particle are all aligned in the same way, especially if it's a crystalline material, obviously. But as they start to get towards the surface, we'll get some sort of irregularities or molecules in the wrong place. And so anything where that system is not homogeneous is effectively counted as the surface. One way of characterising surface energy is we give it units, and the units are millijoules per metre squared. Now it might not be immediately apparent why surface energy has those units, and so we're going to look at where surfaces come from so you can understand the derivation of those units in just a second. But one thing to notice that is, in nature materials tend to act to minimise their surface. So if you look at this photograph of soap bubbles in close proximity, one soap bubble will always form a perfect sphere. And the reason is because a sphere is that shape which has the minimum surface area to volume ratio. So right there, that tells you that surface formation is energetically unfavourable. Interestingly, when soap bubbles come together, you can see that two soap bubbles touching form a straight line, because at that point the straight line is the way of minimising the point of contact between the two bubbles. It minimises the amount of surface which has been generated. So just looking at nature, you can see that surfaces are an unfavourable thing. From an energetic point of view, unfavourable usually means it requires energy to make it. Okay? Those processes that occur spontaneously are those which lose energy, and those which don't occur spontaneously are those which require energy. Since surface formation appears to be unfavourable, it should lead you to the conclusion that it requires energy to be put in, and that's exactly what happens. So let's look first at the work of cohesion. Cohesion, remember, means two like materials coming together. So the easiest way to consider this is to take one material and split it into two and see what energy was required. So on the screen, same example from the slide before, one large pink rectangle of a homogeneous material, and in order to cut it in half we need to put energy in, and we create two new surfaces as shown on the right. Mathematically, therefore, the work of cohesion is given by the area that we've created multiplied by the energy of that surface, and then we have to recognise there are two of those surfaces, one on the square on the left and one on the square on the right, and so it's 2 times that term. So the work of cohesion is 2 times the area times the energy of that surface that we have created, and hence we end up with units of millijoules per metre squared. The system is similar for adhesion, but just slightly complicated by the fact that adhesion means two dissimilar surfaces. So when we consider where the work of adhesion comes from, we have to remember that we have to start with a material that's got two dissimilar parts to it. So the diagram on the left hand side is both dark purple and pink because it's two dissimilar materials, and in order to create surfaces from those materials we have to pull them apart to create two squares shown on the right hand side, B and C. The mathematical definition for the work of adhesion is actually the same, it's just that we have created two new surfaces, so that's C and B, but we have to remember that we also had a surface existing in the first instance, which is BC, which has been destroyed. And so the work of adhesion is actually the area that's been created multiplied by the energy of surface B plus the energy of surface C, but minus that surface which we had to pull apart, which is BC. So it just makes the definition slightly more complicated. But in both cases, work of adhesion, work of cohesion, the units are millijoules per metre squared. What other factors lead into surface energetics? Because it's not just about pure energy of a surface. So some good ones are electrostatic charges. So when you put powders into a mill and you quickly spin them around and you apply a force, not only can you move molecules around, you can also disrupt those molecules and move electrons from one to another, and the material can become charged. So there's a technical name for that. It's called triboelectrification. Think about when you're at a birthday party and you take a balloon and you rub that balloon up and down your jumper and then you hold it near your hair and your hair is pulled towards the balloon. The reason is because in moving the balloon up and down your jumper, you transferred some of the electrons from the jumper to the balloon and it's become charged. And so when you hold it near your hair is pulled to it because of the electrostatic charge. And the same is true here, in that we can charge a particle by applying a force to it during milling. Electrostatic charges are very powerful, but short range and short acting as well. So when a powder comes straight out of a mill, it can be super electrically charged and stick to absolutely everything. But if we leave it a little while, those electrostatic charges have time to dissipate and the material behaves itself a lot better. The other one to think about is capillary forces. So if we have a lot of water in the atmosphere, so get to high humidities, some of that water is going to condense onto the surface of the powder particles. And if we get enough water condensing on the powder, we can form a bridge, liquid bridge between two particles that are adjacent to each other. And so that's a really tricky situation, because if those two materials are partially amorphous at the surface, water will also act as a plasticizer for that amorphous material and encourage it to recrystallize. So if we have a relative humidity above 65 to 70%, for instance, this becomes the dominant force, more important than electrostatic charges. High humidity is both good and bad. If high humidity is too high, then we get liquid bridging and our particles stick together. But if we have a reasonable humidity, it can also cause electrostatic charges to dissipate. So what that means is, when you take a powder directly out of a mill, once it's been milled, it's going to be a disastrous powder for subsequent handling. It may be electrostatically charged, it's probably got the highest amorphous content, and that amorphous material is going to be the highest energy. So what that means is the powder itself will be very sticky because of the electrostatic charges, and even if those charges were to dissipate in some way, you've still got a highly energetic surface of amorphous materials, so high force of adhesion and a high force of cohesion. So what typically happens in the pharmaceutical industry is that they recognise taking a powder straight out of a mill, it's got really disastrous properties for formulating. So the current strategy would be take the powder from the mill and leave it. You can leave it for a day, 2 days, typically it might even be left for up to a month. And in that month, what you do is you allow the electrostatic charges to dissipate and you allow the amorphous material to relax. You can encourage those processes to happen by raising the humidity of the room. So you take your powder from the mill and you leave it to relax in a relatively high humidity environment. Not as high as 70% and higher, because you don't want liquid bridging. You just want enough water, the electrostatic charges can dissipate and the amorphous material starts to relax. Once you've left that powder for up to a month, you will find it's a much better behaved powder for formulating into a dry powder inhaler system. And that process is called conditioning. So you recognise that the powder as it comes out of the mill does not have the right properties for formulation. So you leave it 1, 2 days, a week, a month under a relatively high humidity to condition it so that it's got much better properties for formulating. One other thing to consider that we've not talked about already is the size of the particles. And size of particles is really important because two particles, when they come together, are only interacting at a small point, and this point of contact right here. This has a consequence because if we have a large drug particle interacting with, say, a rough carrier surface, as shown on the slide, the points of contact will actually be quite small. So imagine that my fist is the drug particle, and then my finger is the surface of one of the bits of carrier. As the drug particle comes down, the point of contact between the drug particle and the carrier is actually very small. It doesn't really matter whether the drug particle itself has a high surface energy, and so it would be adhesive or cohesive if the point of contact is very small, because the majority of the surface isn't actually touching. If you move to the right hand side of the slide, you can see now we have a drug particle touching a smooth surface. Again, as my fist comes down and touches the surface, now you can see there's much more point of contact between the drug particle and the surface. So in that example, the two materials might be the same. Drug particle is the same, the carrier is the same, but the surface morphology is different. On the left hand side you've got a very rough surface, and on the right hand side you've got a very smooth surface. And the consequence of that is that the point of contact between the drug and the carrier will be different. And it's the contact area which makes the real difference into how strongly the drug particle is binding to the surface of the carrier. The situation gets worse when the morphology of the surface becomes bigger than the powder particles you're trying to adhere or cohere to it. So if you drop down, bottom row but right hand side, now you've got a very irregular surface but with really big irregularities, much bigger than the size of the drug particle you're trying to adhere to it. And you can see that in this instance the drug particle has gone between the cavity on the surface of the carrier, and so the point of contact is even higher because now there are 2 points of contact on either side. And in the worst case scenario, the topography of the surface matches the topography of your powder particle, and they really do have a massive point of interaction. That would be very difficult to remove that drug particle. Yeah. So last thing in this lecture is simply to look at some examples where force of adhesion or force of cohesion affects the way that the dry powder inhaler is working. And I've put the reference on here so you can go and look at this paper should you want to. So the first example shown on the screen in front of you is using two different carriers. So it's a carrier-based system, either lactose, which is the most commonly used carrier, as I've said already, or erythritol, which is a sugar alcohol, so a replacement for lactose. So on the left hand side the graph is showing you the force of adhesion for the drug particle against the carrier. Lactose is shown in black and erythritol is shown in the light grey. Don't worry about the fact that there are numbers 1, 2, 3, 4. That's a function of how that measurement was made. It was made with an atomic force microscope actually, but you can look in the paper and you can see how that measurement is made. It's just 4 repeats of the same thing essentially. The really important thing to recognise is that the force of adhesion between salbutamol and erythritol is always higher than the force of adhesion between salbutamol and lactose. So if you're going to formulate with erythritol as a carrier, you need to remember that as the drug comes down, salbutamol in this case, it will have a higher force of adhesion. So it will be stuck more strongly to erythritol than it is to the lactose. Now, one of the consequences of that, as I think I've said already, is that the patient has to breathe in with enough force to separate the drug from the surface of the carrier. So in this instance, erythritol is a higher energy surface than lactose, and the force of adhesion is higher. That means it's going to be harder for the patient to pull the drug particle off the surface of erythritol relative to the lactose. And if you look on the right hand side of this graph, this is just showing you the fine particle distribution or fine particle fraction, they're both shown, for lactose or erythritol, and you can see that the FPF for lactose formulation is higher than the FPF for erythritol for precisely that reason. The force of adhesion is higher, so less of that drug is coming off when it's inhaled. The last example is just to show you don't have to worry only about amorphous materials at the surface of your particles. The physical form also matters when we're looking at polymorphs. So this is an example. Again, the paper is referenced on the slide, so you can go and look at it. Salmeterol zinophoate, which has two polymorphs, form 1 and form 2. Form 1 is the stable form, form 2 is the metastable. They're both crystalline, but remember, metastable means higher energy. So what that means is form 2 is going to have a higher force of adhesion than form 1 because it has a higher surface energy. Remember, higher force of adhesion to the carrier means it's harder to pull that drug from the surface. So the graph is showing you fine particle fraction for two formulations, one with form 1 and one with form 2. And again, you can see form 1 has a much higher fine particle fraction than form 2 because it was much easier to pull form 1 from the surface of the carrier than form 2. So, what does this mean? One thing, it means we're at the end of the lecture, so that's a good thing. But it also means that you have to review what it is that we've learnt and then reinforce it by reading around the subject. I want you to remember, dry powder inhaler formulations are based on one of two formulation strategies. That's either agglomerated powder or carrier-based systems. Agglomerated powder is based on a force of cohesion, and carrier-based systems are based on a force of adhesion. In order to get drugs into the lung, we need them to have a small particle size, typically between 2 and 7 microns, but we normally aim for around 5 microns. And those are extremely difficult to make. They're usually made by particle size reduction, which in the pharmaceutical industry is generally a mill. It can be either air jet mill or a ball mill. But however it's milled, milling usually changes the surface of the material from a crystalline material to an amorphous material. Even though the amount of amorphous material might be low, it's located at the surface of the particles, and particles interact through their surfaces. So small amount of amorphous content leads to a disproportionately large effect on the way the powder behaves. When a powder is taken from a mill, it's generally a very badly performing powder from the point of view of formulation. It's probably electrostatic, and it's almost certainly going to be partially amorphous, and so it's going to have a very high surface energy and be both very adhesive and very cohesive. So in order to formulate a milled powder into a dry powder inhaler, the powder is usually conditioned prior to formulation. In that way, we make sure we get the best performing product that we can, or at least the most stable performing product, because it shouldn't be changing with time. And it's really important that you understand how the physical form of the material that you're formulating in a dry powder inhaler impacts the way the product is formulated.